You all had asked for a couple example problems that we didn't get to in class, so I thought it'd be a good idea to give you a video of the solutions. So the first is number 47 of chapter 4. Two crates of mass 65 kilograms and 125 kilograms are in contact and at rest on a horizontal surface. A 650 Newton force is exerted on the 65 kilogram crate. If the coefficient of kinetic friction is 0.18, calculate the acceleration of the system and the force that each crate exerts on the other, then repeat with the crates reversed. So we're going to have to assume that that coefficient of kinetic friction, 0.18, is for both of the crates between either or both crate and the surface. Otherwise, we would need more information. And so we can answer part A by considering the pair of crates as if they were one large crate, since it's the same surface and the same effect of the force. And then I can show you how to do it with consideration of each crate individually. So we have a single crate with mass 65 and 125, so 190. And we consider a single push of 650 newtons to the right. This is not a free body diagram. I'm just trying to reimagine the problem as a single box or crate. So now to the free body diagram, the crate is a dot, and all forces begin at the dot. So that 650 Newton force is to the right. That's the push. I know that the surface, maybe it's a countertop, supports that crate. I'll label that F subscript N for normal force. And gravity is pulling on the crate in the downward direction. And I sure tried to make those equal in length, but I don't think they actually are. So I'll put the little hatch marks to indicate that they're equal in length. And since we're given a coefficient of kinetic friction, we can expect kinetic friction to be involved. And so I know kinetic friction will oppose this motion, F sub k, for kinetic friction to the left, opposing the 650 Newton force. Okay, so we want to know what is the acceleration of the system. Newton's second law says the acceleration is equal to net force divided by mass. Acceleration using positive to right is 650 minus Fk divided by the mass of the block, and that's the combined mass of 190. We then, of course, remember that Fk, my hand's in the way, Fk is equal to mu sub k times normal force. And in this case, because it's a horizontal surface, that normal force is equal to mg, where mass, again, is the 190 kilograms. So I can substitute this now into my equation for acceleration. So acceleration is equal to 650. I'll drop that unit of newtons because we know it's newtons. Mu sub k mg divided by m. 650 minus 0.18. I'm just checking the number. 0.18 times 190 times 9.8 over 190. And this is unitless. This is kilograms. This is meters per second squared. So I have newtons for 650, kilograms meters per second squared, which are also newtons. All of that's divided by kilograms. So I'm left with units of meters per second squared, which is consistent with acceleration. I'm having to use my calculator my phone as a calculator. So I have to unlock the phone every time I need to do a calculation. 650 minus, I have to turn it sideways too, I guess. I missed my calculator. So 650 minus the quantity of 0.18 times 190 times 9.8, close parentheses, 335. I sure don't trust this calculator. 335.16 by 190. So 1.764, as we discussed, units of meters per second squared. I guess I can check the solutions to see if that's an acceptable answer. the solutions in line with, no, I don't think so. What is going on here? Okay, it looks like the solution to 47, the solution to problem 47 is marked in the solutions manual as number 48. Okay, and so the acceleration given by the solution is 1.75, no, 1.7 meters per second squared. So we'll not worry about rounding errors. Okay, so this is an acceptable solution for the acceleration. And again, we considered the solution, or we considered this problem, or reconsidered it, as if a single force, a single external force of 650 was pushing on a larger crate with total mass 190, and then we figured out what friction would be involved there. So now for part B, we can't consider the system to be a single block. Now we have to consider the small and the large block, because we want to know what force does the small block exert on the big block, and then in turn, what force does the big block exert on the small block. So we're looking now at the action and reaction forces exerted by these blocks on each other. So the 65 kilogram block is being pushed with 650 newtons of force. Because of that 650 newtons of force, the 65 kilogram block in turn is pushing on the 125 kilogram block. The 650 is not the force on the 125, but because of the 650 push, 65 is pushing on 125. So I could call it F1 on 2. And then Newton's third law says that whenever there's an action, there's an equal and opposite reaction. So if block 1 pushes on block 2, immediately, simultaneously, block 2 pushes back on block 1. So we have two different forces on two different blocks that are exerted as a result of 1 being pushed up against 2 with that 650 Newton force. So in order to figure out what that internal force is, we need to look at the free body diagrams of each block individually. So I'm going to label them 1 and 2 as I have up here. 1 for 65, 2 for 125. 65 gets 650 newtons to the right. And then there's that push back of 2 pushing back on 1, because 2 is essentially in 1's way. There's a normal force pushing up. I'm going to label it Fn1 to be clear that it's the normal force on block 1 only, and the pull of gravity on block 1 only. And we know these two should be in balance. There's also, of course, a little bit of friction on block 1 because it's sliding to the right. I then consider block 2. It has a normal force. It's bigger because it has more mass. It has a pull of gravity, bigger because it has more mass. Then F21 has an action-reaction pair, and I'll try to draw that with equal length. F1 on 2 is equal and opposite to action-reaction to F2 on 1, and we should figure out a way to highlight that because we want to be super clear that that's Newton's third law happening there. So I'm making them pink, as they are in the diagram above. Okay, and then block 2 is only touching block 1, so that 650 isn't exerted on block 2. This is a horizontal force, and then there's, of course, friction on block 2 because it's interacting with the tabletop or whatever it is it's sliding across. So now I can apply Newton's second law to either or both blocks. I can say acceleration of block 1, 650 to the right, minus F21 to the left, minus, because it's also to the left, the kinetic friction of block 1 divided by the mass of block 1, and or acceleration of block 2 is equal to the right, F12 minus friction on block 2 divided by block 2's mass. So we know the acceleration from part A. Acceleration is 1.764 meters per second squared. And just looking at the two equations, the block 2 equation has fewer terms. So I'm going to go ahead and solve the